Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah wa ba'd. Welcome everyone, and thank you for participating in the KFBM forum organized by the Interdisciplinary Center of Hydrogen and Energy Storage at KFBM and organized by the Carbon Capture and Utilization and Storage team about solutions for carbon mitigation. So my name is Mahmoud Abdel Nabi, research scientist here at Hydrogen Energy Storage. In this meeting, we have 4 sessions starting at 4 p.m. and we intend to finish at 6 p.m. Once the session starts, you will be able to send the questions using the questions function of the Zoom. We will try to respond to as many questions as we can in the slot time of this section. We will begin this forum with the first talk by Dr. Ayman Elbaz, Senior Research Scientist, Clean Combustion Research Center at KAUST, Saudi Arabia. This talk will focus on the opportunities and challenges of ammonia combustion from fundamentals to applications. In the second talk, Dr. Abdullah Shohail, College of Petroleum Engineering Geoscience at KFBM. In this talk, Dr. Abdullah will give us a general overview of the CCS technology, and then we'll discuss in some details the various aspects of the storage components of CCS. The third talk will be given by Mr. Kyle Cordova, Executive Director of Scientific Research Sector, Senior Assistant to the President for Scientific Affairs at the Royal Scientific Society at Jordan. He will give us an overview on the reticular materials for chemical fixation of carbon dioxide. The fourth talk will be delivered by Dr. Edward West, Principal Research Associate at Sorption Technology Center at Air Products, USA, and also here at DTV Center. He will discuss the industrial scale adsorption processes for carbon dioxide capture. As a short introduction, the carbon capture, utilization, and storage CCUS will play an important role in achieving sustainable energy futures net zero emissions goals. In 2022, the Kingdom of Saudi Arabia hosted the G20 summit, highlighting the growing need for circular carbon economy approach. So how does CCUS work? CCUS technology captures CO2 emissions at the source or directly from the air. CO2 emissions are then transported away or stored underground or turned into useful products. Here at the Interdisciplinary Center of Hydrogen and Energy Storage, we believe that with the brightest minds working in CCUS, we can drive the technology and collaboration needed to address the global emission challenge. So let's welcome Dr. Ayman Elbaz. Dr. Ayman obtained his PhD as short introduction, Dr. Ayman.
Thank you.
Obtained his PhD, PhD degree in mechanical power engineering from Helwan University, Cairo, in 2008. He has a Fulbright visiting assistant professor grant at Faculty of Engineering, Vanderbilt University, USA, in 2009 up to 2010. There, he developed a laser diagnostic technique to measure the flow velocity in a supersonic environment into molecular tagging velocimetry technique for supersonic flow measurements. Then he joined Helwan University as an assistant professor in 2011 before joining KAUST CCRC in 2013. Dr. Elbaz took his position of research scientist at KAUST, and recently he got promoted to senior research scientist in the CCRC at KAUST. Welcome, Dr. Ayman. You can start your session.
Yeah, thank you. Okay, so let's see. So now everyone can see my screen, right?
Yes.
Yeah, so this starts directly, and thank you very much for your nice introduction. This is Ayman Elbaz. I am from Clean Combustion Research Center, KAUST. And my talk today is about energy sector decarbonization and the challenges and opportunities of ammonia application. So this is the layout of my talk. We will talk about the background, fundamental of ammonia combustion in microgas turbine, and I will end up by conclusion. So first, let's see, as the people from working in combustion, we are so proud. What about introduce in the energy sector? Because 80% of the world energy conversion now is coming from the combustion. The other thing is, once the people understand the fire, the civilization starts and industrial revolution starts to appear. Let's see. So the industrial revolution, including heating, lighting, internal combustion engines, and also the supersonic pipe flight. So, but the people working with the fossil fuels nowadays is facing a problem with the big challenging regarding the harmful emissions coming from the combustion of hydrocarbon fuels. This is an example in USA. You can see that the major portion coming from the combustion source leads to CO₂ from industrial, electricity, and transportation. And this means we have an increase in the CO₂ level, and this can lead to increasing the temperature of the earth. With this can lead to some environmental change, and this can leads to the climate change. We can see the increase of the sea level. We can see the extreme change in the atmosphere. So, does the people working with the internal combustion engines, prime mover, will stand and stop up till Tesla? And we know Tesla are introducing the electric vehicles, will take the market, or the question is, there will be a game changer. I think we will have some game changer in near future. So the issue is, if people are thinking about using some renewable resource like solar energy, wind energy, the main issue with these sources of energy is the intermittency. So it is not a continuous. So we need to store the energy. We need to store the energy. So if you would like to make decarbonization of the energy sector, it depends on renewable changes. And we need to have energy security from one side and to minimize the environmental effect. And to introduce the energy security, we need a media, and this media can store large quantity of energy and large distribution of this energy. If we look to this plot here, on the x-axis we have a power, and on the y-axis we have the storage time. So if we talk, for example, if we would like to store the energy in the solar capacitor, it can cover up to 100 megawatt, but it is for few seconds. But if you go in the vertical direction in this way, if you look to this blue one, you can see we can store the energy in energy dense fuel. And this can cover from 100 kilowatt up to 1000 megawatt. And you can store the energy in methane, hydrogen, and ammonia. Keep in mind, we don't like to store the energy in methane because it is a hydrocarbon. So we are looking for storing the energy in the hydrogen or the ammonia. And in this model, ammonia appear as a key energy carrier for application for low carbon energy storage and transportation and power generation. It is NH3, it is the ammonia. So some people are talking about, okay, the electric vehicle will replace the internal combustion engines, but this plot can prove that up to 2040, around 33% only for the electric vehicle will be on the road, and the rest is internal combustion engines. So why we are going or focus on the ammonia? The ammonia has different advantages. Look, let's see this figure. If you look to this figure, it represents the different fuels available. And in the x-axis, we have gravimetric density. I know there is a wide spectrum of audience from different backgrounds, so I will try to make this very simple. So if the gravimetric density, it is how many megajoule I can produce by burning 1 kilogram, versus on the y-axis, how many megajoule I can produce by 1 liter of my fuel. This is a different fuel, and if you look here, this is the ammonia. So the ammonia has a higher volumetric density relative to methane and also relative to liquid hydrogen. So this gives advantages of the ammonia. So the ammonia has 45% higher volumetric density compared to hydrogen, 45 compared to liquid hydrogen. Also, it has 17.6% of hydrogen by weight. If you, in terms of cost, 30 times cheaper than the hydrogen per energy unit. You can liquefy ammonia at 8 bar, relative to higher pressures for the hydrogen. This gives some advantages of the ammonia. Let's make as a story. Okay, we have now some features of the ammonia. What is the role of the ammonia? How could I produce the ammonia? How could I use the ammonia in the energy system? This plot gives us like the introduction of the ammonia. How could I produce the ammonia? The ammonia mainly is produced through steam reforming of methane or natural gas. And then we have here syngas. And if you use the CO₂ sequestration, you will have the blue hydrogen. So we have hydrogen and we can produce the nitrogen from the air. So using the Haber-Bosch system, you can compress hydrogen and nitrogen and make ammonia. This is one way. The other way of producing ammonia depends on renewable resources. So you can use these renewable resources to make the water electrolysis and have the hydrogen and then produce the ammonia. This is the production sector of the ammonia. What about the transportation? I think the ammonia, it is in our life like 100 years ago. So the experience of using ammonia transportation, using the same pipeline we are using for LPG or natural gas, we can use ships, we can use the tankers to produce the ammonia. This is well-known experience. About the utilization, ammonia has 2 ways of utilization. You can use the NH3 decomposition to produce hydrogen again, and then you can use the hydrogen in the fuel cell or can use the hydrogen in the power generation. The other way, which I am leaning to, it is the direct use of the ammonia. This one, we can use the ammonia since it contains a higher percentage of hydrogen. We can use the ammonia directly in internal combustion engines, in the gas turbine, and in furnaces, and even we can use the ammonia in the residential application. So this is the role of the ammonia. We know now in July 2020, the Air Product and Aqua Power and NEOM signed a big agreement for a 5 billion production facility in NEOM to produce green hydrogen. And this is the aim of this project, will to produce 650 tons per day of carbon-free hydrogen. We call it green hydrogen for transportation. And this will be like saving around 3 million tons per year of CO₂. NEOM is located in the north west of the Saudi Arabia, and there is wind energy. There will be solar energy. They will be used to electrolyze the water, and then we can produce the ammonia or hydrogen and export it. And the first shipment of the blue ammonia to Japan from Saudi Arabia, it is about 40 tons. This has happened at 2020, 40 ton shipping to Japan. Let's see an example of the spreading of ammonia application, for example, in Japan. In 2011, following the accident of the Fukushima nuclear power plant, all the nuclear power plants in Japan were shut down. Since this date, 85% of the electricity in Japan has been generated from the fossil fuel. But in 2014, a new national project appeared in Japan to replace to use the energy carriers and go to the green hydrogen, or using the hydrogen in the energy sector. So they are producing the hydrogen, the same thing from the steam reforming or from renewable resources, and then how could you move the hydrogen to the like power plant and this? So you can use liquid hydrogen or transfer the hydrogen into ammonia, and then using the ammonia as a direct fuel, or reproduce the hydrogen again from the ammonia. And I think now they have 1 micro gas turbine in Japan running on the ammonia. This is a power plant. They have 1 ton cylinder storage, and they have using the regenerative power plant, so they can vaporize the ammonia, and they are using this in the gas turbine. There is a spreading of using ammonia as a co-fire with other fuels in Japan right now. So the question is, do we able to use the ammonia directly in our facilities like a gas turbine or internal combustion engines, or we need to make a modification on this facility, or we need to make a modification of the ammonia properties? To answer this question, we need to understand that the ammonia flames is different, or compare the ammonia flame with the hydrogen flame or CH4 flame, methane flames. So in a summary, you can see here the heat release from the ammonia. It is less than the heat release from the hydrogen and less than the heat release coming from the methane. The flame temperature, the adiabatic flame temperature of the ammonia is very low relative to the hydrogen or methane. Also, the flame thickness or the size of the flame of the ammonia is bigger. So this means we need to make some modification in the facility or improve the properties of the ammonia flame. So based on that, we can say that the ammonia features very different combustion properties compared to the hydrocarbons. The first, the low flammability limit. What I mean by low flammability limit, it is the lower fuel to air ratio to the higher fuel to air ratio. It is very limited compared to the hydrocarbon. Also, low energy density. You can produce like 18.6 megajoule per kilogram of the ammonia versus it's very low relative to the hydrocarbon. Also, the higher ignition energy. If you would like to ignite the ammonia, you need to increase the temperature up to like 930 degree K versus 964 methane, and higher NO. The emissions of the NO from ammonia is higher relative to the hydrocarbon. To give like an example of this, you can see this plot. This plot gives us flame speed versus different fuels. What I mean by flame speed, if you have an internal combustion engine and you have the spark, so the flame is propagating to burn the unburned mixtures. So it is related to the flame speed. You can see the flame speed of the ammonia is very low relative to the other hydrocarbon fuel. It is around 7 centimeters per second relative to the hydrogen. You can see in this plot. Also, the extinction strain rate of the ammonia is very low relative to the other hydrocarbons. The flame size of the ammonia is very big. So this means we need to think, or we need to do some improvement of the properties of the ammonia. This is why we need to go to the fundamentals of ammonia combustion and understand this. To do this here in CAUS, we have different facilities. We have different experimental methods. We have spherical pump, and this we can measure through the spherical pump. You can capture the flame properties at higher temperature, but low pressure. And also, we can capture the flame properties at engine condition, like higher pressure and higher temperature, using what we call RCM. Different techniques, but at the aim of this different technique is to characterize the flame of the ammonia. So let's see how could we improve the ammonia combustion characteristics. One of the way of improving ammonia combustion characteristics, increasing the flame speed, increasing the reactivity, is to blend ammonia with high reactive fuels. And if you look to the literature, you will find that ammonia blending with hydrogen, ammonia blending with methane, natural gas, syngas, it is there to improve the combustion characteristics. Here, I will give one example of blending ammonia with DMM. DMM is produced from methanol. So the methanol is the building block of oxygenated fuel. So if we are talking about oxygenated fuel, you can blend, the oxygenated fuel has a higher reactivity. So we test this blending ammonia with DMM. And why DMM? DMM can be produced also from renewable resources. So we are introducing a blend of ammonia and DMM, which can be produced from renewable resources. Let's see. And this is a test facility. We just mix the mixture of the ammonia and the DMM in this chamber and ignite and evaluate the flame speed. How could we improve the flame speed of the ammonia? And this is a running condition. I will not go through the details of this condition. However, we can see here, this is the flame speed. This is the video here showing that the flame speed of the pure ammonia at 5 bar, and this is the flame speed of pure DMM at 5 bar. You can see this one is very slow relative to the fast flame speed, we can get it from DMM. So blending ammonia and NH3 with the DMM can enhance the flame speed. As we can see in this plot, this is a flame speed of 20% DMM relative to the ammonia. And once you increase the DMM in the blend, it enhances the flame speed. So the propagation of the flame will be faster. Why this has happened? Because if you introduce a higher percentage of DMM in the blend, this introduce free radicals of OH, O, and H, which is enhancing the flame speed based on these free radicals. Increasing the DMM, increase these free radicals, enhance the flame speed. And this is just summary to show the blend in the literature. You can see this is the XM means how much percentage of the enhancement fuels relative to the ammonia, starting from pure ammonia to 100% of the methane or hydrogen. So this is the methane enhancement in the flame speed. When you increase the percentage of the methane, of course, the flame speed is increasing. Also, this is the DMM, and the higher enhancement you can see when you blend the ammonia with the hydrogen. So one way of improving the flame propagation of the ammonia is to mix the ammonia with a higher reactive fuels, and this is example shows the different reactive fuels we can blend it with the ammonia. The other thing is if you are talking about the ignition delay time. What I mean by ignition delay time? Ignition delay time when you compress the mixture at higher pressure and higher temperature. How long it will take to ignite. This is we call ignition delay time. And this is very important in internal combustion engines. We know that the ammonia has a long ignition delay time. And if you look to this plot here, this is the ignition delay time relative to different hydrocarbon fuel here. So you can see that we have a long ignition delay time of ammonia and a short ignition delay time of the other hydrocarbon fuel. The question is, how could you move this plot to be close to the fuel we are using in internal combustion engines? So I will show this example of blending ammonia with the DME. This is the ignition delay time. It is low of the DME, and this is the ignition delay time of the ammonia. So if we blend DME with the ammonia with different blend, you can see this is the plots. So here, lower percentage of DME, it's around 0.05% DME. This is again pure ammonia. This is DME 0.05, and here 0.1% DME in ammonia, and here it is around 0.5% DME in the ammonia. It looks like when you are increasing the DME in the ammonia percentage, you are decreasing the ignition delay time, the time used to ignite the mixture. And if you put here, this is the first fuel, gasoline fuel. So this is the ignition delay time of it. So this means you see these red dots here or stars, it is at 0.% DME in the ammonia. It matches the same ignition delay time of the phase fuel F of the fuel. This means this blend can simulate the same condition or combustion characteristics of the fuel we are using in internal combustion engine in terms of ignition delay time. And okay, one of the issue of burning ammonia is the NOx formation. And this plot shows the ammonia when you burn ammonia in two conditions. One can lead to higher NOx emissions when you burn ammonia in lean condition. What I mean by lean condition, you are increasing the oxygen content in your fuel. So this will lead a higher NO2 condition and NOx formation. But if you burn ammonia in rich conditions, this can lead to De-NOx. It means in decreasing the NOx formation in the ammonia combustion. This leads people to think about, okay, so this means in the flame, we would like to burn ammonia in the rich condition, but rich conditions means your combustion efficiency will be low. So they are introducing staged combustion. This means you are burning the flame in rich condition, and then in the downstream, you can introduce the air. So overall, it will be lean. You have a higher combustion efficiency, but you are reducing the NOx. This is technique the people are studying now to burn ammonia and reducing at the same time the NOx formation. Okay, so based on this background, so we understand that the combustion characteristics of ammonia is different than the hydrocarbon fuel. We know blending ammonia with different fuels can improve the combustion characteristics of the ammonia. How could we go to the ammonia combustion in microgas turbine? Actually, we start. Yes.
Yeah, we have 3 minutes, inshallah.
Okay. Okay. I will try to finalize very fast. Okay.
Thank you very much.
So we have here the swirling flame in our lab, and we start to burn ammonia with different hydrocarbon fuel, methane flames, and we start to characterize the flame in terms of how could we get the flame stability versus the ammonia percentage in our flame. And we are able to introduce a higher percent of 100% flame with the ammonia and a stable regime. And this is the NEOM emissions. This is another thing. Let's go because the time is here. This is a microgas turbine. This is available microgas turbine. How could we introduce the ammonia to this? That's what we are doing right now. We get an Untitled microgas turbine, and to test this to use the ammonia in Untitled microgas turbine, we build what we call a reduced scale burner, because the size of the burner, we cannot put this size of the burner in our high pressure combustion duct. So we design a simulated of the microgas turbine and this simulated burner here. So if you would like to get this small burner simulated, the actual one, we would like to do some large edge simulation to get the same flow rate and the same flow pattern inside the reduced scale burner and the prototype one. And this is what we are doing right now in KAUST. And this is our reduced scale burner of the microgas turbines. This is the design of our burner. And here, this is the component. And we start to get some result of this burner using the reduced scale burner. Okay. So another example, recently from the lab, we are now introducing the double stage burner using ammonia in these flames. And here some flames with the ammonia, swirling flames with the ammonia, 40% ammonia up to 50% ammonia. And this is our flame when we are using the ammonia in our lab. I think I will just introduce new or important number. Maybe people will ask about it. What is the cost of the ammonia? NH3 has a cost per unit energy around $0.5 per kilogram for hydrogen, relative to $15 per kilogram of hydrogen. Producing ammonia from green producing green hydrogen is 3 times higher cost relative to the normal fossil fuels route. And the main cost of producing the ammonia is coming from the price of the natural gas. 70 to 90% of the ammonia cost is coming from the price of the natural gas, as indicated in this part. This is ammonia decomposition. This is another hot topic, I think, now. If you would like to reduce the hydrogen from the ammonia, what is the catalysts you would like to use? And this is one of the projects we are running right now in KAUST. In a conclusion, I will end up with this conclusion that apart from energy transportation and storage, I think ammonia will be used in the power generation directly. The main advantage of using ammonia directly is no need to hydrogen decomposition and purification of the ammonia. Blending ammonia with a different blend will enhance and boost the combustion properties of the ammonia. Partial cracking of the ammonia will be also one of the possible way to increase the combustion characteristics of the ammonia. Also, new strategies are needed to mitigate the NEOM emissions, such as staged combustion or very lean combustion of the ammonia will be needed to reduce the NEOM emissions. With this, I just would like to thank our colleagues here in KAUST for producing such work on the ammonia. And with this, thank you very much.
Thank you very much, Dr. Ayman, for the fantastic presentation and talk. Actually, we have now questions from Abdulaziz Al-Qahtani. He is asking if we use NOx re-education technology in combustion system, can we decrease the NOx emitted by the ammonia?
Yeah. I think using ammonia, it is one of the put it in the what we call exhaust treatment to reduce the NOx. But the NOx coming from the ammonia, it is a fuel NOx. It is not a thermal NOx. So the treatment of NOx coming from ammonia, it should be chemistry. You would like to treat you would like to burn the ammonia in rich condition, and then you introduce the lean condition further downstream of the flame.
Yes, thank you very much. Second question from Dr. Muhammad Ali Ihsan. He's asking about the unhealthy issues, I mean the safety issues related to the process of the ammonia, its smell and corrosion causing properties.
Yeah. I think this is a good question. The main issue is handling ammonia and working with the ammonia. The people has the experience and the tools using the ammonia, handling transportation of the ammonia. It is already exist. Regarding the corrosion, I think it is still under testing, and we have some neutralization experiment now on how the effect of the ammonia on different materials. This is, I think, one of the area we need to cover it.
Yeah, thank you, Doctor. Third question actually is related to, I think, the process itself. Can these concepts be used in the pumps? I don't know actually what's related, which concept exactly, but maybe the process of combustion he means. This is from, his name is not sure.
No, I didn't get the question or the meaning.
Yeah, me too.
If he can just send it to me or give him my email, we can discuss this in details. Yeah.
Yes, thank you very much. Actually, I don't have more questions. So, yeah, last one. How we can, yeah, from the chat, how we can I contact Dr. Ayman? Yeah, we'll share this, and it's of course with the, I mean, registration, you will see the contact emails, and we can share, and Dr. Ayman also can share his email, inshallah, for everyone who is interested for more discussion. Thank you very much for Dr. Ayman for the talk. Thank you for fantastic presentation.
Thank
you. So now, inshallah, we can shift for the second session, which will be led by Dr. Abdullah. So a short introduction for Dr. Abdullah. He's an assistant professor of geophysics at College of Petroleum Engineering and Geosciences at KFPM. He earned his BSc degree in geophysics from KFPM, master and PhD degree from University of Calgary. Dr. Abdullah was a visiting scholar at Stanford University between 2012 and 2013. He led and co-led several carbon capture and storage projects and initiatives during his postgraduate and professional career, including the Pembina Cardium CO₂-EOR pilot projects and Weyburn-Midale area CO₂ sequestration project, WASP, and site selection monitoring under TIC CCS. The center was before in KFPM. He also contributed to consortia, Stanford Center for Carbon Storage, SCS, workshops and educational courses focusing on CCUS and CCS. Dr. Abdullah is a member of several professional societies, including the Society of Exploration Geophysics, SEG, and other community and other society. So thanks and welcome, Dr. Abdullah. You can start.
Thank you very much. I would like to start by thanking you and the Center for Hydrogen and Energy Storage for the invitation. It's such an honor to be amongst you this afternoon. And well, I mean, let's just dive right into it. So the way I planned this presentation is to be, as the title implies, so it's more of an overview of geological storage. And I do apologize in advance for some of you finding this a bit trivial, but I just wanted to kind of touch on the different aspects of the storage, and hopefully that will be informative to the audience. So I'd like to start with this slide, and let me see if I can. Okay, All right. So we have to start up at some point. So I would like to start from this slide because it tells a number of things. First of all, you'll notice during the talk that I'll be using carbon and carbon dioxide interchangeably. And we know this is not true, but this is something that frequently in scientific communication, we kind of interchangeably use words. So I would like to point this out. So with the carbon cycle, there is a difference between carbon and carbon dioxide, obviously. The second thing here, the terms storage and sequestration. I specifically chose storage for my talk because, at least in my opinion, I think of the sequestration as a broader term that encompasses not only geologic storage that involves carbon capture, but also sequestration in the natural system, like you see here in the ocean, and the soil, and the trees. And also sometimes we tend to artificially enhance the sequestration, the natural system sequestration of CO2. For example, you might have heard of a startup called Vista, in which they're using a mineral called olivine, which is basically a magnesium, iron, oxygen kind of mix, and mineral made of those elements. And basically, they're doing what we call a natural sequestration of CO2. So they're enhancing through weathering the way we absorb carbon. So that's one example that's more related to the geology, but I won't be talking about this. I will be talking more about the subsurface storage in geologic formation. Another type of storage that I'll be not talking about today is, for example, sequestration of CO2 and mine tailing, which is quite interesting if you think about it, especially with the mining development and the kingdom aiming for mining to be the third pillar of the economy. That will bring a lot of challenges. So the greenhouse gas effect, I think you're all familiar with this. So basically the incoming solar radiation, part of it is reflected from the atmosphere, part of it is makes it to the surface and then reflected as an infrared. And with the increasing greenhouse gases, the amount of heat trapped will increase. And the way scientists use, or the term scientists use or the metric scientists use to characterize this increase in the heat influx into the earth is the radiative forcing. And basically you see here the greenhouse gases sitting at the top here with the kind of red-coded color. You notice some of also the human induced particles and molecules also contribute, but in this way an actually cooling effect. But there is an interesting behavior between the two, but I'll keep that maybe for another discussion. So back to the CCS. So this is a look at one of the let's say analysis undertaken by the International Energy Agency, and you'll find many of those by the IEA and CCS Institute and others. And basically we're looking at the different scenarios in terms of reducing emissions and an outlook as we navigate the 21st century under the Paris Agreement, which if you're watching the news, you might have seen an article a couple of days about that the 1.5 degrees Celsius target is actually projected to be reached sooner than anticipated or than what was hoped. So anyways, I want to draw your attention here to the CCS, which sits here under fuel switch, CCS and US and others. And you'll see that it contributes, I mean, the percentage would vary, but some put it around 10%, 15%. So that kind of tells you that moving into the future, CCS or CCUS would need to be included as part of a comprehensive portfolio. But that, of course, depends on the country's specific. Some countries do not have really infrastructure for hydrocarbon. They don't have huge sedimentary basin. So we're talking here about percentage globally, but definitely there will be some countries that for such countries, CCS wouldn't be a viable option at all. But overall, we're talking about 10% or so. So why is it essential? Well, to achieve decarbonization and definitely the climate change reduction or the emission reduction targets, enable clean hydrogen. You've heard from Dr. Ayman about the green hydrogen. We're talking here more about blue hydrogen. So blue hydrogen would involve CCS, but definitely moving into the future. And this is, I think, one of the areas in which Saudi Aramco is putting a lot of emphasis and investment navigating the future under the Paris Agreement. A low carbon dispatchable, so basically CCS could enable us to tap into fossil fuel with low emission or maybe even zero emissions, and negative emission. And I think this is very important because in the future, it's looking into the future, it's very hard to think of a negative emission scenario without carbon storage. That's something, at least the way I look at it. In terms of economic growth, creating and sustaining jobs, especially in countries like the Kingdom, in which the fossil fuel industry is a major driver of the economy. Of course, the new net zero targets and the innovation spillovers that will be spilled over to other sectors of the economy. And the just transition, and I think that relates very closely to the first one. And of course, keeping infrastructure news, which is also important, especially for countries that are still having their infrastructure being developed, and it's too late now to switch back or to stop these developments. So in terms of the components, we have the capture, transport, and storage. And later in the storage, or even actually before we start injecting, we look at what we call monitoring, measurements, and verification. And I'll try to touch on this later on. So again, the different components here involving CCS, and in terms of the value chain, I think this is something I would like, if I have time, I'll come to it later. So basically, here is a look at the cost overall. So you see the cost varying from different projects, different areas. For example, you see the Boundary Dam project here in Canada, Bitronova in Texas. So you'll see the range of costs, ranging between $30, $25 to around $110. And a lot of research is being undertaken to bring that cost down using not only the conventionally known techniques, pre, post, and oxy-fuel, but also looking at things like modular systems for carbon capture. So in terms of the cost, I know it is very important to touch on the cost. So here is a breakdown of the different components and the cost involved. So typically, if you combine the compression with the capture, it's around 75%. The pipeline would cost around 10% of the overall. And then the storage, which also depends, are you talking about an onshore or offshore aquifer? Okay. So in terms of the cost and the uncertainties, so here we have some comparison between the two. So in terms of the capture, I will not spend time here. I think that's beyond the scope, but I just want to throw this slide, as I mentioned earlier, in terms of the different components for the capture. The transport, so it's either pipeline or through ships, basically. And here is an example of an existing infrastructure that could be used in CCS. In terms of the cost, that kind of plays down as a function of distance and other parameters as well. So moving into the storage. So when you talk about the storage, there are many different aspects or different options. There are obviously CO₂ for EOR, and I'll touch on this later on. But the hugest potential, according to many studies, are actually saline aquifers. You see here something resembling coal bed methane, and this is also interesting, but the potential for such geologic formation is very low because of the constraint on the permeability, porosity, and the scale of these coal bed methanes and the cost involved in developing them and injecting into them. So in terms of the characteristics of CO₂ storage, what are the things we're looking at? Capacity, injectivity, containment, safety, and cost. And of course, leakage comes as a very important aspect of CCS. So here is a look at the prospective storage in sedimentary basin globally. And in terms of the storage, stationary point sources, here is a look at the thickness of sedimentary basins. Now here we look at basically the storage capacity, and this is more of a kind of prospective theoretical storage capacity. But just to put things in perspective, in total, in the Middle East, it is estimated that we have a capacity of around 3,454 gigatons. To put this in perspective, our annual emissions of CO₂ around 38 or 37 billion tons of CO₂. So that kind of put things in perspective in terms of the capacity and the importance of CCS. So in terms of the storage, as we said, we move from kind of perspective to more of operational storage. Storage indicator in terms of the development, in terms of the capacity. You see Saudi Arabia, for example, here sitting closer to 100 gigatons, which is quite significant. In terms of projects here in the kingdom, we have a project used to be called Ammonia, CO₂-EOR, but now they call it Saudi Aramco CO₂-EOR demonstration project. I think they're capturing around 800,000 tons of CO2, and they're injecting it into Ghawar, basically into Ammonia, which is part of Ghawar field. And here is a look, a map view of the injection and the production wells, as well as some observation wells. Here is kind of nice cartoon showing kind of animation of what's happening there. Now that is only a tiny bit of the Ghawar field. Now imagine the capacity the kingdom holds in terms of oil and gas fields and saline aquifers, which we haven't really explored for that. So looking at the CO2 phase diagram here, and I want to emphasize that we're looking at CO2 in a sense or in supercritical phase, and that is because it has this important behavior. So if you look at the supercritical phase, the density here has something in between a gas and a liquid. So why we're interested in density, for example, I think that I will illustrate in a couple of slides. But here is a look at the life cycle of a CCS project in general. So it goes from pre-selection all the way through the development, injection, and post-injection. And with it comes many important activities that we have to undertake. So we usually start with a basin, identifying subregions, zooming in into site selection, and then on certain areas, we do the site characterization. Among the questions that we have to ask, there are many things that we have to explore. Here is an example of an initial site characterization. Obviously, not only technical data, but societal and economical data, and a lot of important aspects that goes into there. Now, in terms of the basin characteristics or the criteria, we have what you call a hard criteria. For example, you want to sit away from tectonically active areas. There are semi-hard criteria. These are that can be enhanced to some extent or can be worked around in a sense. And then we have soft criteria, which are very fluid and can be adjusted, like public acceptance of CCS. In terms of the criteria, there is a list of different things that we look at. But if I zoom into the density, as I mentioned earlier, so here we're looking at CO2 in supercritical phase. So typically at this stage, due to the pressure and temperature, the CO2 volume will be substantially reduced, and that actually plays into our advantage in terms of the storage itself. Now, this has another implication, is that we can store more as we go deeper, but of course there is a limit. But also, as carbon dioxide leaks into the surface or into the shallower subsurface, it starts expanding, and that makes it more detectable for our MMV techniques. Again, a multidisciplinary approach. Here is a kind of simple kind of diagram showing the interaction between the different disciplines we saw earlier. But of course, we cannot really find the perfect site. So always there are uncertainties involved, and sometimes it's important to capitalize on our understanding or existing knowledge of the subsurface. Once we look at those criteria that we looked earlier, which is one of the criteria used globally, then we can sort the basins in terms of scores. For example, one here indicates a very suitable site, and in this case, we're looking at relatively cold geothermal system, oil and gas infrastructure, major CO2 sources, and tectonically passive zone where we don't expect to have earthquakes. So in terms of the storage, here is something that captures some of the critical elements in the subsurface storage. And these are the reservoir itself and the cap rock. So for the reservoir, we look for reservoirs that have high porosity and permeability. Porosity plays into the capacity, and permeability plays into the injectivity. So if you can reach both, then you would have, or if you can find a reservoir that satisfies both conditions, then you have reached, or you have found a very good candidate for CCS. For the cap rock, of course, it could have high porosity, like shale, but the important thing is the permeability. So we don't want our cap rock to be permeable or faulted or suffering from some fractures. So in terms of the trapping mechanisms, we can divide them broadly into physical and chemical trapping. Now you see here, based on this diagram by the IPCC, is that the physical throbbing dominates at the beginning, but with time, the chemical throbbing will take over. But of course, we know this is not entirely true. I mean, through research and accidents, we found that there are, instances where actually carbon dioxide will be mineralized within a time frame of years, just years. And that's quite interesting. And one of the projects in which this was found is the Carbon Fix project in Iceland. They were injecting carbon as part of the carbon sequestration or CCS activities. And they noticed that they're missing a lot of carbon that comes, or they don't see the carbon where they expected. And they noticed that actually some of the carbon is being mineralized at a very fast rate in the reservoir. So looking at kind of different storage or throbbing mechanisms here. So here are some examples of a fault which could act into our advantage. Now we might ask, of course, this poses some risk. Maybe some of the carbon dioxide will leak through this fault. So there are possibilities of this happening. But in oil and gas field, we have found that if the fault is very well constructed geometrically and it's in a very passive zone, then that has held the hydrocarbon for 100 or 10 millions of years. So that is kind of elevated. Here is a very famous kind of anticline, like what we're sitting here on the Hran, the Dammam Dome. And here are some examples of an unconformity and a pinch out, which is a type of stratigraphic throbbing. Hydrodynamic throbbing is different from the structural and stratigraphic in a way that it doesn't have a four-way closure. So the carbon can move with the hydrodynamic system or regime, but that will take tens or 100 millions of years for it to keep moving in the subsurface. Residual throbbing, so yes?
Yeah, 3 minutes, inshallah.
3 minutes, okay. So I'll probably just maybe skip through some aspects here as probably we've discussed them. So I want to skip to some aspects here related to the injectivity and storativity. So in terms of the capacity here, we mentioned the capacity being an important factor. And how do we go about estimating the capacity? Of course, it depends on many parameters, including the effective porosity, basically the amount of pore volume that is available for us in the subsurface. So this is one way we could estimate the storage capacity that you saw earlier in some of the slides earlier. And now the porosity can be complicated, and with it comes many uncertainties. And here is an area where you can tap into things like machine learning and deep learning and trying to predict and minimize the uncertainties involved. Saturation, again, another important parameter, but another critical parameter is the injectivity itself, which is a function of the effective permeability of the medium. And that is extremely important because you could have large volume for storage, but if you cannot inject at a rate at which you receive the carbon dioxide from the capture facility, then you've got a problem. So you need to keep a nice kind of flow of the incoming captured carbon dioxide. Okay, so that's an example. So the movement in the subsurface can be quite complex, as you can see here. For EOR, so I'll just focus on the use of carbon dioxide for EOR here. I'll just show you an example. And actually, I showed you an example area with the Saudi Aramco CO₂-EOR project in Saudi Arabia. But here is another project in Weyburn, which is one of the industrial scale project among the first project to be undertaken. And there are many things that are happening here. Obviously, we don't have time to talk about them, but one of them is the miscibility, is the CO₂ being mixed with the oil in the reservoir in a miscible or immiscible way. Another thing is the mobility ratio, and another factor is also what we call the wettability. So for example, if you look at the mobility ratio, and essentially what we want to do is enhance the mobility ratio. So that if we decrease M here, we can enhance the sweep efficiency and thus recover more oil. Here are some examples here. So you see a nice scenario where M is less than 1, and here you see some kind of fingering effect as a result of the high mobility ratio. Looking at an example of CO₂-EOR, so this is the project in Weyburn-Midale project in Saskatchewan and Canada. And again, they're using CO₂ for enhanced oil recovery. So here you can see that over time, the initial recovery was going through basic water flooding, like what we do now in Ghawar. We have a very, very young or young fields here in Saudi Arabia. We are fortunate, alhamdulillah. So later, as the depletion started, they start to increment with vertical, horizontal. But you notice here how the contribution of carbon dioxide is the contribution it's making. And it is estimated that that will add up around 115 million barrels throughout the lifetime and increase the lifespan of the project by 15 to 20 years. In terms of the MMV, I don't think I'll have time to go through them, but I'll just mention or just show you an example. Of course, there are many risks associated with carbon capture and storage. So we're looking at local and global, of course. There are strategies that we can undertake to devise an MMV plan. There are examples. I'll show you an example from the seismic. Being a geophysicist, I'm a bit biased maybe toward the seismic. But in terms of the cost-benefit analysis, you see that 4D seismic sits at a very high cost, but the benefits are very high. So skipping through these just for the sake of time, I'll move to the example. So this is I think one of the earliest project that involved, or actually the earliest that involved CCS for non-EOR. And in this case, the Statoil was capturing the carbon from the East Leibner field and separating the carbon and injecting it into the Utsira formation. And that is for many purposes, including avoiding taxes by the Norwegian government. So here is an example of the images or of the monitoring that we could undertake to monitor the activities on the site. So here is a time plane view, and here is a cross-sectional view of the showing the seismic data over the injection site. So here is obviously before any injection. As we inject, the plume expands, of course, migrating due to buoyancy, among other factors. And with that, the bloom will grow and will show more and more on the seismic data. Of course, not all sites will behave in a similar way. If we have a tight onshore aquifer or reservoir, that probably will not show as much response as we see here. So in terms of the pressure and injectivity, obviously in depleted reservoir, there is a depletion of the pressure. So once we start the injection, we're a much better status when it comes to pressure, unlike saline aquifer, which might tend to have some pressure buildup, so we might need some pressure relief with time. Interaction, this is between different wells. This is something we have to keep in mind as well. And in terms of the conceptual risk here, so you can see that the risk increases as we start, and after we stop, the risk gradually decreases, and then that would affirm, or that would make the, let's say, the regulators more comfortable with taking over the responsibility of post-closure. So I'll close with these few slides, if you allow me, Mahmoud. So this is I haven't talked about the cost and the feasibility of CCS in a global perspective. So I saved those for later, but here look at what you call the abatement cost. And what is the interesting thing here to notice is that the abatement potential of these technologies sitting toward the right here is huge. So you're talking about gigatons of CO2 equivalent. And unfortunately, the cost is high, but the reward is high as well. So I think many people in the CCS and researchers and the CCS community are trying to work hard to bring the cost down, while, of course, the storage contribution or the abatement potential will remain high there. Now, in terms of CCS itself, it varies, really depends. For example, if you're looking at capture from natural gas processing, it sits actually among the lowest, maybe as low as $25 per ton of CO2 capture. Now, as you move into heavy industry like iron and steel or cement, the costs start build up. Of course, you have heard of the direct air capture, and that sits in the order of a few $100s per ton captured. So again, different options, different technologies, where to invest or which one to emphasize. That is something to be seen in the future, where regulators and investors will divest or direct their investment. In terms of the risk, obviously, you'll notice that here we're looking at CO2 injection oil fields. So the risk is very low because we very much know these fields. We've collected a lot of data. We've been analyzing them for decades, and we have very good understanding of what's going down there. But the challenge is with saline aquifers, because these we don't really develop, we don't study quite often because of the lack of resources per se in these aquifers. Just to close up with these last two slides.
Yes,
so you heard about the circular carbon economy, and which is really part of this circular economy concept, going from linear to circularity. And I think with that, with the endorsement of the G20, as Mahmoud mentioned, when the event was hosted in Saudi Arabia in 2020, you see that CCE, circular carbon economy, is being adopted by the G20 members, and that only makes, let's say, the outlook for CCS more and more promising as we embrace CCS as a part of a bigger framework that involves the circular carbon economy. And with that, I would like to thank you all for your time and for listening. Apologize, Mahmoud, for taking.
Thank you very much. Yeah, thank you very much, Dr. Abdullah. It was very interesting talk, actually, and I think also it will interest for the all attendees. But let's go for questions quickly. I think Dr. Ayman has one question. So, Dr. Ayman, let's start with this Q&A note. Yep. So, first one from Mudaina asking, how can we apply aerogel technology as CCS method in Saudi Arabia? Especially it considered as a successful method in recycling and capturing? Okay, so you're talking about using aerogel in a form for storage? Yes. Okay. Definitely, I mean, anything that could contribute to the storage potential in terms of, you know, essentially we're dealing with emulsions and colloid and stuff like that. So aerogels, if it enhances, for instance, the miscibility in hydrocarbon reservoirs, for example, for EOR, which is quite extensive resources that we have here, then definitely that's something. But aside from that, I don't have much to add to aerogel because I'm not really much into those colloids. But yeah, thank you very much, Dr. Abdullah. Second questions from Abdullah Zamil. He's asking about injection CO2 into natural gas wells and seeing how much the natural gas comes out. So, I mean, in like the resourcing of EOR, but in case of natural gas. While CO2 stays in, how can I estimate how much natural gas will come out and the dose? Is it efficient or not?
Okay. So, for example, if you look at an oil recovery, enhanced oil recovery, they estimate that a ton of carbon dioxide, it would take a ton or 2 to 3 tons of CO2 to enhance the recovery by 1 ton or 1 barrel, of oil. So in terms of natural gas, it depends, of course, on the system. I don't have specific number to give, but I think it depends a lot on the specificity of the reservoir itself, and that is a function of many different parameters. So I can't give an exact number, but in terms of oil, I'm more familiar with the numbers in general. Yes, and I think there is miscibility issues with different gases. Maybe will happen underground. I'm sure also I'm not right. So third one, I think Dr. Ayman.
Yes.
You can go, Dr. Ayman.
Yeah, it is just a question for Dr. Abdullah. How do he evaluate the cryogenic carbon capture as a technique of the carbon capturing? Sorry, how do I evaluate? Sorry, what? The cryogenic carbon capture?
Yeah. Okay. So I'm not quite, I don't know, to be honest with you. Yeah. I don't have an answer to you for that one. Okay. Yeah.
I mean, from efficiency, Dr. Ayman, maybe is a problem with the cost, I think.
Yeah. Okay.
Yeah, this is associated because you need much energy or more energy for cryogenic. But the process will be similar, I think so. Yeah, maybe. So thank you again, Dr. Abdullah. Let's go for third question quickly. What's the life for CO2 to be mineralized? I think maybe the lifetime, or this is a question. Life one for CO2. I mean the time for mineralization.
Yeah. So as we saw in the kind of trapping mechanism slide, the time frame that was initially kind of anticipated or predicted by researchers that was included in the IPCC report in 2005, was looking at something in the order of hundreds of years. And that's actually quite, let's say, true when you look at sedimentary basins. But one thing that wasn't considered there is that what happens if we inject carbon dioxide into basalt, which is a kind of ultramafic rock. And in these rocks, it turned out that due to the composition and also, for example, in Iceland, the geothermal regime played and the thermodynamic system played a role in that as well. So in that case, they noticed it's happening in a matter of years, a couple of years. They captured, or they actually mineralized, a substantial amount of the carbon that was being injected into the formation. So now that kind of stimulated the question, can we do this in sedimentary basins? Can we devise some kind of catalyst to accelerate the process of mineralization? And that is an interesting question. I think some people looked at this. Now, of course, it comes back to, as you mentioned, Dr. Ayman, the concept of cost. Is it feasible? How much this material will cost? And how the dynamic will play in the reservoir as well with these materials. So it's certainly an interesting question that will take a lot of the risk associated with the leakage, which I haven't had time to talk about, but that could take many different forms through abandoned walls or through faults or through capillary forces. So definitely that's an interesting question, and I think we'll see more research into how we can accelerate mineralization.
Thank you again, Dr. Abdullah. I think it's the time now for session 3. Maybe one or two questions we can answer it outside, inshallah. So now let's welcome Mr. Kyle Cordova again. So for the third session, this under the reticular materials for chemical fixation of carbon dioxide. So Mr. Kyle Cordova is Executive Director for Scientific Research and Senior Assistant to Her Royal Highness Princess Sumaya bint Al Hassan for Scientific Affairs at Royal Scientific Society at Jordan, and an adjunct professor in the Department of Chemistry at the University Putra, Malaysia. Mr. Kyle received his graduate degree in inorganic chemistry from University of California, Los Angeles, UCLA. He was a founding leader of the University of California, Berkeley Global Science Institute, BGSI. During his tenure at BGSI, Mr. Kyle was responsible for designing, implementing, and managing all the global science centers in the United States and abroad, including Japan, South Korea, Saudi Arabia, United Arab Emirates, Kuwait, Jordan, and China, and Malaysia, and others. So he was actually global leader for this institute. Kyle has received a number of awards, including being named as leaders in innovation fellow from the Newton Fund and UK Royal Academy of Engineering, International Union of Pure and Applied Chemistry, IUPAC, US Young Observer from the US National Academies of Science, Engineering, and Medicine, Ronald E. McNair Scholar and US National Cancer Institute Scholar. He has recently founded his first spin-off company, AquaPro Venture, to commercialize his research discoveries for water application. His company won the Queen Rania National Entrepreneurship Competition and UNICEF Water Sanitation and Hygiene Entrepreneurship Competition. So interesting topic, inshallah, from Mr. Kyle. Let's welcome again. You can start.
Thank you very much, Mahmoud. I'm very excited to be here. I spent 4 years at KFUPM, and I'm very happy to be back, and I'm very honored that you would invite me for this. So I'm going to talk today about particular materials for chemical fixation of carbon dioxide. There's a lot that I've done in carbon dioxide transformation and utilization, but I felt that since I'm talking to KFUPM, I want to highlight all of the wonderful work that has been done in CENT, formerly CENT. I know it's not CENT anymore, but yeah. So what do I mean by, say it again?
Yeah, hydrogen energy storage. That means previous name.
Yes, yeah. I know it's a new name. But what do I mean by reticular? What do I mean by reticular materials? I mean metal organic frameworks, or MOFs, or zeolitic and mesozoic frameworks, or ZIFs. And the basic concept for designing these materials is that all reticular materials are entirely composed of joints and links. And so here you see a drawing by the famous artist Escher, where you see these cubes right here that are the joints, and they're connected by these links. And if you have a little bit of chemistry knowledge, you can kind of convert those shapes and those links, those joints and those links into actual chemical species, and link them up into extended periodic frameworks that have a lot of porosity, and that porosity can be tuned for specific applications. When we talk about carbon dioxide fixation, we first have to capture the carbon dioxide. So I want to first highlight here a wonderful paper that we published together at KFUPM. This is Professor Othman Al-Hammouz in the Department of Chemistry, and this is Dr. Mahmoud, who's here with us today. I call him my Sheikh, Sheikh Mahmoud. But in this paper, we developed microporous organic polymers, and we identified a number of different criteria that were important when you wanted to develop or design new CO2 capture materials. And so the first one is that it has to have a high absorption capacity. You don't want to create a material that can't capture a lot of CO2. The second is selectivity. We know that at any point source, whether even if that's direct air capture from air or for post-combustion flue gas, or even for other processes, pre-combustion, you have to be selective towards CO2 versus the other components in the gaseous mixture. The third criterion is that it have to have fast absorption kinetics, so it has to absorb and desorb quickly so that you can continuously process those gas streams. You want to have mild regeneration. You don't want to have a big energy penalty like you see with monoethanolamine solutions that are currently used in industry. You want to have long-term stability. You want to have tolerance to other components, especially if you're trying to purify, say, methane, you want to capture CO2, something like H2S could cause a problem. And you want to have low production cost if you want to actually make this happen. And so what we have identified for the different classes of, solid porous materials is that really MOFs and ZIFs meet a lot of these criteria in a very exceptional fashion. And there's numbers behind all of this, the reason why we say that they're exceptional achievement, but this is what you want to keep in mind. And so recently we've been looking at designing new zeolitic and metazoic frameworks. In zeolites, in order to access high porosity and appropriate pore channels, you really go after designing the membered rings. And among zeolites, 3-membered rings are really, really important. But this concept in ZIFs, in the metal organic analogs of zeolites, has really not been explored. We can make all sorts of membered rings, 4, 5, 6, etc. But 3-membered rings are difficult because of that ring strain. And so what we found out was that when you look at a tetrahedral site like you see right here, and you have your imidazolate bonding those tetrahedral sites, there's 2 different angles, what we call theta 1 and theta 2. And if they're within a certain degrees, keeping in mind that the tetrahedral site has to be 109.5, then you can start to systematically and rationally design the total membered ring of that zeolitic and metazoite framework. And so if you look in the literature at all of the different ZIFs reported, they all fall within 132 to 150 degree angles. And if we want to get to 3-membered rings, we have to get below that 132 degrees in order to compensate for that ring strain. And so we typically take, ZIFs are taken inspiration from zeolites, where you have silicon, oxygen, silicon bond of 145 degrees. And your tetrahedral, which is usually a zinc 2 plus imidazole tetrahedral, is around 135 to 145, actually 132 to 150. But if you look at porous germanates, where that angle is actually smaller, down to 130 degrees, the analog of an imidazolate, which is this triazolate, actually achieves smaller angles, around 120 to 130 degrees. And so we set out to do that. We took a zinc 2 plus salt, and we mixed benzotriazole with different functionalized benzimidazoles, and we actually were able to generate these 3-membered rings that were then linked into an extended structure. And what we saw in those 3-membered rings is that we always have a 2-to-1 ratio, either 2 benzotriazoles to 1 benzimidazolate, or 2 benzimidazolates to 1 benzotriazolate. And so the reason why I'm showing you this is because we had a research scientist with us when I was at KFUPM named Abdul Hadi Al-Zarani. He's now, I think, in the US doing his PhD. But he was the first one to crystallize these structures, which we call NPO ZIFs. And so here you see the crystal structure of the 3-membered ring, and you see it in a reduced form. And the overall topology is what this NPO, which is similar to in zeolites. And you have these beautiful one-dimensional channels that are made up by 2 different cages. And so we call this ZIF 1001. This is actually a sort of a funny story. We're collaborating with Chinese colleagues in Shanghai Tech. And we asked, well, what do you want to name this one? And the Chinese said, well, let's do 1001 for 1001 Arabian Nights, because it was invented in Saudi Arabia. So I thought that was cute, and now it's called ZIF 1001. But it's not just to design them. We actually then test the different adsorption isotherms. So here you're seeing CO2 and nitrogen on one plot, CO2 at 3 different temperatures. And you can see that there's significantly higher adsorption for CO2 than there is for nitrogen, which means that there's a high selectivity when you actually calculate it and you fit the isotherms. And it's nitrogen phobic because it doesn't absorb any sort of nitrogen. That's all great. This is a thermodynamic static measurement, but we wanted to test it in an actual dynamic setting. So this is what's called a breakthrough experiment, where we fill a column and then we mix gases together, flow that through the column, and then monitor the effluent by either a GC or a mass spec. And so here you see nitrogen and CO2 under water, because water typically likes to compete with CO2. And you see that the breakthrough of CO2 is significantly longer, so it holds that CO2 into the column, while the nitrogen just sort of passes through. And water doesn't affect it at all. Over 5 cycles, we have the same exact breakthrough time. Great, we can do it for 3 different gases. But what happens when we actually do flue gas, when we have a lot more gases? We have SOx, we have NOx, we have oxygen, and many other components. And so we actually we got flue gas from an industry, and we tested this material, and we have the same exact breakthrough time. And over 30 cycles, we don't see any sort of decrease in performance. And so this is a really, really exciting thing. We've submitted the paper, and that's that. So that's about CO2 capture. But this whole talk is about CO2 fixation. So in MOFs, if you want to do CO2 fixation, you have to understand the different structural features that are important. I just realized my camera's not on. Sorry about that. You have to know what structural features are important. And so the first one is defect-driven catalysis. And I'll show an example of that later. And what I mean by defects is that you either have a linker, organic linker vacancy, or you have what's called a Lewis acid defect. The second structural feature is an inorganic SPU-driven catalysis. So this is something like site-isolated metals or metal oxides on an extended framework. The third sort of structural feature is linker-promoted catalysis, where the organic linker actually does the catalysis, or you can have some sort of combination between the organic and the inorganic in the MOF. And so my first sort of dive into this field is creating these materials in Vietnam, where we choose this hexatopic organic linker with zirconium, and we mix that with zirconium, and we form 2 different structures, or with indium. The structures are actually quite beautiful. They're 3-dimensional. They have high surface area with accessible metal clusters. This is the actual topology. How do you get that topology? Well, the organic linker only bonds to 4 of its carboxylic acids. 2 of its carboxylic acids are free, so it forms actually a rectangle. The metal cluster forms a trigonal prism. And so when you see this column, or this pore channel, if you rotate it 90 degrees, you can see the open free carboxylic acids that did not bind to the metal center. And so we took this, and we took either an olefin, or we took directly an epoxide with CO2 to see if we can catalyze CO2 in the formation of cyclic organic carbonates. And we found that we can get up to 96% conversion, 86% selectivity, and 82% yield at mild conditions of 80 degrees Celsius and 1 ATM. And so we looked at the mechanism, and we tried to understand whether it was Lewis acid or Bronsted acid sites that played a critical role. And we found out that actually it was both. And these are my 2 students in Vietnam, Phung and Hung. When you dehydrate the material, you actually form an open metal site where the epoxide interacts with. We have a co-catalyst N-butyl ammonium bromide that comes and does a nucleophilic attack, opens the ring. CO2 comes and inserts in between that. And then you have a ring closing, kicking out the bromine to regenerate the co-catalyst and generate the cyclic organic carbonate. Similarly, on the free carboxylic acid, the epoxide can interact through a hydrogen bond. The co-catalyst does the same thing. It acts as a nucleophile, backsides attack, ring opens it, CO2 inserts, and then it closes, kicking out the bromine to regenerate the co-catalyst and the cyclic organic carbonate. That's very exciting, but we really wanted to understand which one was the preferential catalytic site. And so what we did, or before I did that, we did this multiple times. We cycled this, the conversion, the selectivity, the yield basically stayed the same over 5 cycles. And so this was an exciting result. We did a 1-pot synthesis where we took a olefin, right here, styrene. plus CO2 plus an oxidant, which is tert-butyl hydroperoxide. We threw them all together in one pot with the MOF and the co-catalyst N-butyl ammonium bromide. And we ran this reaction again. And so what we see with MOF 892 is that at the low temperature, we see a high conversion, a relatively good selectivity and yield of 180 and 80. When you compare that to other MOFs that were well known for this reaction, we significantly outperform them, especially going one step forward where we don't actually have the epoxide. So we generate the epoxide in situ through this reaction. To show the different sites, like I was saying before, we actually methylated or protected the two carboxylic acids that did not participate in the MOF formation. And so here's a digestion NMR where we show that we successfully post-synthetically modified or esterified the carboxylic acid. We have the same sort of structure. We have a drop in surface area, but that's to be expected. And we have a little bit less CO2 uptake for the protected MOF 892 versus the pristine parent MOF 892. And when we run that through the catalysis again, we see that the conversion, the selectivity, the yield stay relatively high, which means that those free carboxylic acids are not the dominant site. It's actually the Lewis acid sites that are the predominant catalytic site. So that zirconium that is dehydrated upon heating. Next, I want to show you a little story about Dr. Asif Halal, who I think is here with us today, another scientist at KFUPM, and Dr. Nazir Saman. And so, like I told you, a structural feature that we can sort of exploit is defect engineering. And what he did was very, very smart. He took a zirconium cluster that is known in UIO66. This is the linker, benzene dicarboxylic acid, and mixed it with a second linker that only had a monocarboxylic acid and an alkylamine right here. And the reason why he did that is instead of these carboxylic acids binding to the metal inorganic cluster, the other side, the alkylamine, actually then forms a defect. And so what he did was he loaded that at 10, 20, and 30, and 40%. And he saw, which as we would expect, that more defects leads to larger pore sizes. This is a pore size distribution. And then he did a 3-component cycle addition of CO2 with aniline and 1,2-epoxyhexane with all of these different catalysts. As the defects increase, he actually sees an increase in the yield because you have now more Lewis acid sites for those reactions to happen. And this is a bioactive oxazolidinone, I can never say that word, I'm sorry, Asif. And he took different substituents of both the oxide and the aniline with different electron withdrawing or different electron donating effects, and he studied these. But he found that all mono-substituted aliphatic and aromatic epoxides produced ultra-high yields of the corresponding product with up to 78 to 90% yields and quantitative conversion. Finally, I just kind of want to end on a brief point is that you can then go to photocatalysis or photoreduction of CO2 using MOF catalysts. And so over the years, there's been a series of developments, what I call different generations of these photocatalysts that are used for CO2 reduction. The first was focused on selectivity and activity. And what I mean by that is they site isolate photoactive units, whether that's from the inorganic building block or they stitch onto the backbone of the organic linker a photoactive coordination compound like this rhenium or manganese coordination compound. That was used as the catalyst. They played with the surface area in terms of the pore metrics and the internal surface area. And they also started to use MOFs that had coordinatively unsaturated metal sites that a CO2 can come bond to, and then the photocatalysis can happen through that. That was the first generation. That was the early days of MOF photocatalysts. The second generation was really focused on photonic efficiency, increasing the light absorption process. And what I mean by that is band gap engineering. So playing and adding different functional groups to the organic linker or extending the pi system of the backbone in order to play with the electronic character of the linker. They also wrapped MOFs around plasmonic nanoparticles like the silver nanocube in order to intensify near surface electric fields so that the photocatalysis and the photonic efficiency could be increased. The final generation, which I think where we're currently at, is the electronic efficiency where they add a photosensitizer And all of these sort of strategies are well known in other solid state fields, but they're new to MOFs. And so these are exciting developments. So they use this root BIPI where you can generate long excited state lifetime to enhance the quantum yield. You do a little bit of doping. So you take a zirconium cluster, you add in a titanium in order to modify the electronic character of the SBU. And I think now what people are working on, especially the Dinka group at MIT, is trying to improve the orbital overlap between the metal and the linker. So what I mean by that is changing from an oxygen metal bond to a thiolate or an amidate or a semiquinone in order to ensure that you have better charge transport. In a paper that we wrote when I was at Berkeley in 2018, we sort of identified what we thought the ultimate solution for CO2 photo reduction by MOFs was, and this sort of a system would have the following characteristics. It would have a metal cluster, or what we call a secondary building unit, that has efficient electron transfer to CO2. So you have something like iron, cobalt, or copper. You add inside of the pores a photosensitizer, like I showed you in the last slide, the root BIPI, in order to enhance the quantum yield. You want to have that SBU that has iron, cobalt, or copper to have coordinatively unsaturated sites, so the CO2 can come and bond there and accept the electrons. And then, like I talked about in the fourth generation, you want to have that good orbital overlap between the metal and the linkage so that you can have efficient charge transport. And if you really wanted to be fancy, you can put it in plasmonic nanoparticles, and you want to have a single crystal so that the light can be absorbed. So with that, I'd like to acknowledge the scholars behind the success. I had a number of good colleagues at UC Berkeley that helped me with my global science endeavors, like Dr. Hiroyasu Furukawa and Dr. Chris Trickett. The Vietnamese were the ones that worked on that hexatopic linker, and I thank you, and this is them in 2015. But really, a lot of the work that I showed today was in Saudi Arabia. I'd like to thank Professor Zain Yamani, who was instrumental in making sure that we had all of the resources, and he established really a good group when CENT was there. Dr. Asif Halal and Mahmoud and Othman were some of the work I showed, and UBL was with that ZIFS. Finally, I'm here in Jordan working to build up a research lab and a research unit and helping the country really transform its research culture. And this is our group last year in 2021, and we have wonderful support from Prince Hassan and Princess Sumaya, and a fantastic group of emerging scholars that are working tirelessly to propel themselves first and foremost, and some of the chemistry behind MOFs. And with that, I'd just like to thank some of the funders. And Mahmoud, I think I'm pretty good on time. I'm happy to take some questions.
Yeah, thank you very much, Kyle. It's interesting talk again, as usual. So let's start with questions. Maybe the first here, I think Ahmed Aloush is asking for MOF 892. Do you believe there is a function for the MOF itself, or its similar catalytic activity might be achieved using a molecular zirconium cluster? So is the framework has a huge effect, or it can be simple clusters, as it also might have the capping agent effect?
Yeah, so in that study, we also checked metal salts and small metal oxides, and we saw that the conditions that we used did not produce the same conversion selectivities and yields as we see with the MOF. I think really what it came down to was those defect sites, those Lewis acid sites from the zirconium. When the water was removed, that's the catalytic site. And because you have a high density of those catalytic sites, you're able to achieve the sort of values that we saw at the conditions that we ran them in. Is that Aloush, my Aloush, or a different Aloush?
Yeah, he's the one, yes.
Okay. Aloush, you need to finish up your PhD. Yalla.
Yeah. So next one, can you elaborate on scaling up? I think this is interesting. Most of the people want to hear about that, scaling up of mass production of using MOF, especially for the photocatalysis process.
Yeah, I mean, the photocatalysis MOFs to scale up would be very challenging at this point because they're complex systems, right? And they usually take complex linkers, and you have different components inside of the pores. In terms of scaling up MOFs in general, some of the early generation MOFs that were good for hydrogen storage or methane storage, or even recently water harvesting, this is being done by large companies all over the world. I usually have a slide to show all of the different companies doing it, and they can produce them on ton scale. There's a number of different startups that are now producing them on 100 kilogram scale, different designer MOFs. So I think this is just it's just an industrial adoption problem now. It's not a scaling problem. But for the photocatalysis or photocatalytic MOFs, that would be a little bit challenging because the linkers that you use are very fancy and quite complex.
Yeah, thank you. I think the interesting is that how we can combine mass production with the cost, because this is industrial challenge, because production of reproduce the MOF, I think it can be happen easily, but the point of scaling with the cost, this is the challenge.
So I think, as you mentioned, I have a company that I'm working on, and we're scaling MOFs, and the price really comes down to just the metal salt. We can do most things in water now, so we've removed the solvent issue. And if you're able to use it, if you want to scale a MOF, you want to choose a metal that is cheap. So you want to choose aluminum, iron. You don't want to choose something like zirconium or titanium, or maybe titanium's okay, but zirconium or vanadium, or some of these more expensive metals.
Yeah, this actually thanks for Dr. Abdel Abbas, our previous president. He asked that question. Next, actually, the question from Dr. Asif Hilal. He's asking in same MOF 892, is the oxidation and cyclic carbonates formation are in situ?
Yes. Yes, so the third one where I took styrene and the oxidant and CO2, it was all one pot. So you're producing the epoxide, and then the epoxide then is interacting with the CO2 to form the cyclic organic carbonate. And we tried, many different substrates like we did in your paper also.
Yeah, thank you very much. Yeah, I think it is done from now. Maybe something in the chat, but we'll continue, inshallah. Thank you again very much, Mr. Kyle, my old mentor, for that. So, and for the interesting topic about the reticular chemistry and MOFs. So let's shift, inshallah, now for the final talk by Dr. Edward. So Dr. Edward West, he has a BS in chemical engineering from University of Pittsburgh, USA, and a PhD in chemical engineering from University of Massachusetts. Dr. Edward again has worked for air products research and development efforts since 1988. So last 30 years in adsorption technologies, the most expert in the area. He develops process for separation and purification of the gas by adsorption from concept to industrial scale design. His contributions including carbon dioxide capture, hydrogen purification, helium purification, argon purification, and methane upgrading, pretreatment of air prior to cryogenic distillation, and ozone oxygen separation. So most of the gas separation, he is leading the projects in air products for all the gas separation projects. So the talk today will be for the industrial scale adsorption process for the carbon dioxide capture. Welcome to Dr. Edward again. Thank you very much. So, Doctor, you're still mute?
Correct. Now I am not mute. Thank you. Thank you, Dr. Mahmoud. And thank you for the invitation, and thank you for the previous presenters who provided a lot of broad information to us today. So I'm a research engineer at Air Products, as we mentioned. I'm currently this spring spending time with my colleagues at Air Products labs and facilities in the Tehran Techno Valley. As we said, I've been developing adsorption processes for Air Products for about 30 years. And if I can make sure my slides advance.
You can see the slides, but not full screen.
You can see slides, but not full screen.
Yes.
So what do you see? Multiple slides. Let me share a different screen. Maybe that will work for me.
Yeah, now it's okay, Doctor.
Now it's good. Now it's good. Okay.
Yes,
Okay. So I get to consider and understand the adsorption of gas molecules on solid surfaces. I get to work with our engineering group towards turning industrial scale adsorption processes into a reality and everything in between. Air Products is a industrial gas company. And to put it simply, we sell oxygen, nitrogen, and hydrogen primarily. And it's the sale of hydrogen that it's a sale of hydrogen that gives us interest in recovering carbon dioxide. Steam methane reforming is the most efficient process for selling hydrogen, and as the #1 supplier of merchant hydrogen in the world, Air Products generates a lot of carbon dioxide emissions. And because of this fact, Air Products has a goal to decrease our carbon intensity by the measure you can see on the screen by 30% in the next 18 years. The way we're going to do that is we got 5 routes to do it. We're currently a large emitter of carbon dioxide, and we can develop processes to capture that carbon that we're emitting now from our hydrogen plants. We're developing processes for carbon-free hydrogen. We are looking at projects in which we would generate hydrogen from fossil fuel, but with lower carbon emissions. And we want to improve the efficiency of our plants, make them more efficient, will lower our carbon footprint, and Air Products always has its eye on how we can utilize renewable energy to achieve these goals. So adsorption is one method that we're going to use, especially on that first method, to decrease our carbon footprint, and that is to capture carbon dioxide from the plants where we're emitting it now. We have a world-class adsorption technology center, started in 1973 by Shivaji Sarkar, and over the last nearly 50 years, we have characterized hundreds of adsorbents and adsorbent interactions and modeled. Currently, we have 15 chemists and engineers in our group that account for about 200 years of adsorption-related experience. We have complete adsorbent characterization in our labs, and we also have process development systems that allow us to take concepts from lab scale measurements up to industrial scale design. And our primary systems in this are hydrogen PSA, oxygen VSA, nitrogen PSA, and air pre-purification TSA. Another valuable tool we have in Air Products is a dynamic simulator for adsorption processes. Adsorption processes are changing all the time, and this simulator has been verified and validated in its utility over many years. It was started in the late 1980s and became a usable tool by the early 1990s. So adsorption and adsorbents, as Professor Cordoba described, it takes advantage of the fact that porous networks of material in which one component is preferentially adsorbed over another, and these adsorbents can take many forms. Amorphous forms such as activated carbon and activated alumina, up to crystalline forms of zeolites and molecular organic framework materials. And as we saw in the last slide, it is the selectivity of one adsorbate over other adsorbates that make an adsorbent suitable for use in industrial scale. Here I show adsorption capacity for 13X, which is the workhorse of adsorbents in the industrial world. It's a standard adsorbent, can be used in many different processes. And in the graph, I show that its CO2 capacity is far and away more than that of other gases that you'll find in the syngas that we develop in the hydrogen generation process. The other thing about using 13X is to get good working capacity for carbon dioxide is we have to go to very low pressures in order to regenerate the bed. And this is the basis for the process that we're going to put in an industrial scale, a carbon dioxide VSA multi-bed adsorption process. And this picture describes what happens in an industrial process. It's a multi-bed system, and the picture here shows what happens through one bed as it goes through its steps. And the very left will absorb carbon dioxide from a stream, such as syngas or air, which will be at a pressure anywhere from 2 to 50 bar. And as I mentioned before, when we take the carbon dioxide off the adsorbent, we have to pull a vacuum on it to get the good working capacity. And that evacuation step is going to go from anywhere from 0.1 to 0.4 bar A. In between those two pressures, depending what the starting point is, we will have more vessels available so that we can do some depressurization to go from our feed pressure down to our evacuation pressure through steps of pressure equalization. That in the depressurization step, gas from the top of the adsorber column is sent to the top of another adsorber column to repressurize following its regeneration so that it can be used for adsorption again. And the higher the pressure, usually the more benefit you get by having more of these steps of pressure equalization. At one point in the process, though, there are no more vessels to which to send this gas, and we can take it from there and add it to our product stream or vent it. And in this case, we can get a carbon dioxide product of 85 to 99% pure. A more efficient way is to take the gas from that column that remains and is at its second lowest pressure, is to pull the carbon dioxide, which is at a relatively pure but not very pure state, and add it either to the feed or introduce it to a vessel that is undergoing some kind of step in the process. And in this case, we can make carbon dioxide product in the range of 97 to 99.5% pure at relatively high levels of recovery. Air Products is not new to using this kind of process for carbon dioxide adsorption and capture. In 1986 and still operating today, there is a hydrogen PSA system, copyrighted, trademarked as Gemini 9, in which we are capturing a pure hydrogen product and a pure carbon dioxide product. And it's a relatively small amount, 27 tons per day carbon dioxide, but at high purity. Air Products also in the 1990s used this adsorption VSA technology for upgrading landfill gas. In this case, the carbon dioxide is captured and removed from landfill gas. For example, the carbon dioxide in these plants is vented, but it's used for upgrading methane. So we have a basis by which to develop processes for CO2 capture using adsorption. And as I mentioned before, today we want to capture the carbon dioxide that is being emitted from all of our hydrogen plants. And the amount of carbon dioxide emitted per kilogram of hydrogen produced is about 9 kilograms, and that makes for a lot of carbon dioxide being emitted by Air Products today. And this graphic describes the general Air Products steam methane reforming hydrogen process. Steam methane reforming is the most efficient way to make hydrogen, but as I mentioned, it's also a big CO2 emitter. So it is an endothermic reaction that is heat is supplied by natural gas fuel to provide the heat for reaction, usually operating at around 30 bar, and it generates hydrogen, carbon dioxide, unreacted methane, and intermediate gas, carbon monoxide. We can purify this with a hydrogen PSA. The unrecovered hydrogen and the other components are blended with a natural gas fuel to fire the reaction, and the carbon dioxide emission comes out in a flue gas. So we have three places by which to recover this carbon dioxide: a low pressure, relatively low concentration carbon dioxide stream coming out of the flue gas, a low pressure but higher concentration carbon dioxide stream, which is in our hydrogen PSA waste gas, or a high pressure, moderate level carbon dioxide stream, coming out of the reformer before it goes to the hydrogen PSA. We consider all. We looked at capturing carbon dioxide from the tail gas, but found that a more efficient way to do it is to capture this carbon dioxide using a VSA adsorption process from the high pressure gas between the reformer and the hydrogen PSA. And with this, we can get greater than 95% recovery of our carbon dioxide at 99% purity. But it's important to note that this only captures about 60% of the total CO2 that's present in the process. There's still quite a lot of carbon dioxide that comes out of the flue gas. But this process was developed and implemented in our Port Arthur, Texas hydrogen facility. We have two large SMRs in Port Arthur, and between the two of those plants and this carbon dioxide VSA that we're operating, we are capturing 1 million tons per year of carbon dioxide. That system has been operating continuously since 2013, and as I mentioned, 1 million tons per year carbon dioxide. The product is compressed to 150 bar and supplied to a pipeline that's about 8 miles from our Port Arthur plant. It goes to a enhanced oil recovery from Houston through Louisiana to oil fields in Mississippi and Alabama. So as I mentioned before, here we're only recovering 60% of the carbon dioxide that's available. So now Air Products wants to invest some more time, money, effort, development into increasing our ability to capture carbon dioxide in our existing SMR hydrogen plants, but also in our future hydrogen plants. One area that we're looking at is to use a CO2 VSA process to capture the carbon dioxide as it is coming out in the flue gas. More of a challenge because it's wet. It's going to have some SOx and NOx associated with it. It's low concentration and it's low pressure, but it gives us a chance to cover about 95, greater than 95% of the CO2 that Air Products is producing in any one of its SMR plants. Another way to reduce our carbon dioxide emissions is to change our reforming process to that of autothermal reforming. Well, I mentioned steam methane reforming is the most efficient way to generate hydrogen. It has its challenges when you also have to incorporate carbon dioxide capture into the system. A more amenable way to capture carbon dioxide is to use an autothermal reformer. And in this case, we put in a large air separation unit, which generates oxygen, one of Air Products' core technologies. It's added to the natural gas fuel steam, and it's the oxidation of the natural gas within the catalyst, within the gas phase, generates the heat for the reforming reaction. Now, all of our carbon dioxide is contained in this high pressure stream, and there's no flue gas associated with the reactor. Therefore, we can put in a carbon dioxide VSA system to capture carbon dioxide and get around 95% of the total carbon dioxide that's in the system captured. And then I should mention that adsorption is only one way to capture carbon dioxide. When I take a look at these systems, we can also consider amines, partial condensation, and Air Products is going to use the best systems possible. So to put it simply, Air Products is working towards mitigating our carbon dioxide emissions. associated with our hydrogen plants. We are going to continue to be a supplier of hydrogen around the world. And when we have an existing steam methane reforming plant, a CO2 VSA is the preferred way to capture that carbon dioxide. A hydrogen PSA, or I should say a hydrogen plant, is not just a hydrogen plant, it's a hydrogen and steam generating plant. Adding a system such as an amine capture for carbon dioxide becomes problematic because the hydrogen plant is built to provide the amount of steam and the amount of hydrogen that the customer wants, and there is no extra steam. So that's why using electricity to capture the carbon dioxide is the preferred method in an existing plant. If we look at a new steam methane reforming plant, we're going to consider both CO2 VSA and amine systems for capturing the carbon dioxide. But Air Products is going to build new hydrogen plants beyond those just of using the steam methane reforming technology. We're investing a lot in green electrochemical hydrogen generation from seawater, and that project was mentioned earlier in this symposium as what we're going to invest in the NEOM project. And as I mentioned before, we're going to look at hydrogen generation processes from hydrocarbon feedstocks, including biogas and including other off gases, using ATR and some other processes. Air Products is going to consider all the available CO2 separation processes that we know, such as the VSA that I mentioned, amine, and low temperature condensation. And to put it all together, Air Products is a gas processing company, and we have the technology by which to process gases to give us the best and most efficient way to generate blue hydrogen and incorporate carbon dioxide capture into that. And the syngas generation methods, all Air Products technologies or partner technologies are listed on the left, and our means of separation are numerous. We can do adsorption, partial condensation, and amine removal of carbon dioxide. So we have the whole technology portfolio and the ability to choose what's going to be the most efficient process at a given level of carbon capture. To just summarize a few of the opportunities that Air Products is pursuing, we've announced a multi-billion-dollar net zero hydrogen energy complex in Edmonton, Alberta, and in this case, it is an autothermal reformer that's going to generate our hydrogen along with CO2 capture in the scheme I showed earlier. Hydrogen is going to be sent to a pipeline that exists in this region of Canada. And we're also going to make liquid hydrogen there. Air Products is also going to put a net zero hydrogen energy complex in Louisiana with the natural gas gasification as our means of generating hydrogen with CO2 capture and permanent sequestration in the pipeline that is. It's not going to go into the pipeline for enhanced soil recovery. It is going to go into a sequestration reservoir under a lake near New Orleans. And within that plant also, we're going to take the nitrogen from our air separation unit, combine it with our hydrogen to make ammonia. So we're generating blue ammonia in this project as well. And of course, it's already been mentioned that Air Products is investing in the NEOM green hydrogen product using renewable power to convert seawater to hydrogen by electrolysis. So thank you and that hydrogen generated by electrolysis is going to be combined with nitrogen from an Air Products air separation plant, converted to ammonia. Ammonia will be shipped around the world to provide energy throughout. So thank you very much for your attention, and I'll be happy to ask any questions that may come up. Thank you, Dr.
Thank you very much, Dr. Edward, for the interesting talk about the technology, and especially the most relevant to the attendees' interest, how it looks like in industrial scale application. So again, we'll start with questions. First one from Dr. Muhammad Yusuf Khan. He's asking about the fate of the green hydrogen compared to the blue hydrogen in the next future or the near future, 10 years, for example. How we can look for the post technology?
Yes, Air Products sees a future in both, as you saw from the last 3 slides that I've presented. And as we go through the exercises of doing this on the largest scales around, we will be able to improve the efficiency of both methods. You know, Air Products is looking towards generating hydrogen, green hydrogen, but also realizing that there is a need for hydrogen, which is still going to be less expensive, you know, in the short run than green hydrogen. So Air Products wants to go down both avenues.
Yeah, thank you. It's clear. Next one, actually, is Dr. Naif Qasim. He's asking about the VSA that shows excellent CO₂ purity and recovery, which are shown to be 90% or 95%. However, how about the energy consumption compared to the TSA, since some of renewable thermal energy source could be helped in the TSA process?
A TSA process?
Yes, compared to the VSA process.
So I think TSA processes are generally suited, and of course it depends on the adsorbent and their selectivity and the conditions at which you're running it. TSA processes are most suited for removing trace components. You know, in our steam methane reformer effluent, which is also shifted prior to hydrogen PSA, there's about 16% carbon dioxide, and it's not really suited for a TSA process. A better comparison would be that within an amine process. And if we take a look at, you know, an MEA process for capturing the carbon dioxide and then stripping with steam, as opposed to you know, adsorbing with putting over an adsorbent bed and then pulling off that carbon dioxide with the energy associated with a vacuum pump, you know, from an energetic basis, from a capital basis, from a total cost equivalent basis, they come out to be very close. So Air Products takes a look at the environment in the area where we're going to put such a plant and decide which is going to be the best solution. You know, the other thing that comes into play in this is carbon intensity. You know, what fossil fuel are you burning to make that steam or non-fossil fuel? What fossil fuel or non-fossil fuel are you using to generate that electricity? So that's where the comparison from one industrial scale process compared to another lies. It's between amines and adsorption.
Yes, thank you very much. Next one from Dr. Abdul Abbas. He's asking, do you think the liquid hydrogen is going to be economically valuable?
Air Products,
as
yes,
a product?
Yes. Air Products does make and generate liquid hydrogen. We just put in a new hydrogen liquefier in the Gulf Coast of the United States. So where it makes sense economically, Air Products will make liquid hydrogen and ship liquid hydrogen. This is kind of limited to land-based shipping of hydrogen. Shipping of liquid hydrogen overseas is not ready at this point, and that's why Air Products is converting that hydrogen to ammonia for shipping around the world.
As a liquid product. The next one is about Dr. Muhammad Al Ihsan is asking about the separation process in hydrogen separation using the metallic dense membranes. Is it economically valuable compared to the BSD?
Not on the industrial scale, and we know there are dense metallic membranes for making pure hydrogen on the smaller scale, and they will find their place, and Air Products is, you know, evaluating and always keeping its eye out towards methods of hydrogen purification.
Yeah, this is dependent on the process. So last one, from my side, actually, I'm interested to hear your advice regarding the carbon capture, not from the hydrogen production process, but from air, from the direct air. I think if you have, what do you think for direct air capture?
Direct air capture is
Yes.
certainly something that is advancing. It's the cost per kilogram of carbon dioxide is still very high relative to sources that Air Products has a direct interest in. So if we look at Air Products, we want to capture the carbon dioxide that we're emitting now for a variety of reasons, and that's easier to capture than the 400 to 600 ppm that we're going to find in air. But I can see that the technology is improving, materials are improving, processes and ideas are improving, such that the costs for direct air capture are continually coming down over the last 5-6 years. So Air Products is going to keep an eye on that, and when, you know, we have advanced our gas adsorption technology to the point where it's suitable, and materials or others materials are suitable for direct air capture, Air Products will show an interest there. But I have to point out that, you know, Air Products is mainly focused on the carbon dioxide that we are going to emit or don't want to emit in the future.
Thank you very much for the talk and for the summaries that you concluded for our today sessions and forum. So again, I thank my panelists, my speakers, for your valuable time and discussion. Thanks again for all the attendees for your participation of today's forum. And this is, from my side, this is the start. Anyone has any concern, he can contact the center through any electronic channel, website, or even the new Twitter and other channels. You can reach even the speakers at any time. I think they will not mind that. And thank you again. Thank you very much for the fruitful discussion. Thank you.
Thank you.
Thank you.
Thank you very much. Thank you, Dr.
Thanks,
Mahmoud.
Mahmoud. Thank you. Thank you. Bye.
Dr. Mahmoud.
Thank you. Thank you, Dr. Abdullah.
Very nice kind of organization and very nice conduction of the whole event.
Thank you very much.
And it's a pleasure to meet many of the speakers. Dr. Ayman, I haven't had the pleasure of meeting him when he was here at KFUPM. Probably I was doing my PhD or something at that time.
Thank you very much. Yeah.
Dr. Ayman, Edward, and Carl. Always a pleasure. Hopefully we'll meet in person sometime.
Yeah.
Sure.
Yes. Thank you. Thank you, Dr. Mahmoud.
See you soon, inshallah.
Bye-bye.
Bye.